Hey everybody, it's Dr. J, and today, we're talking about valence electrons. Let's talk chemistry. What is valence electrons, right? Valence electrons are electrons with highest principal energy. All right, so basically, this is the electron on the outermost shell. Okay, now the other electrons we call those the core electrons. Now, these are basically going to be in the lower energy shells. Now, Dr. J, why are we starting off with valence electrons? What is valence electrons? Right, just defined it, but why are they important? Well, let's get into that. All right. So, valence electrons is actually the electrons that are going to be very important going forward. You need to understand valence electrons or really know the valence electrons. So, when we're talking about bonding, right, and reactivity, basically everything is impacted by those outermost shells, right? So, for example, I'm gonna give you guys some examples, and then we're gonna go over the periodic table here. But basically, oxygen has six valence electrons. Okay, sodium has one valence electron. Chlorine has seven valence electrons. Is this clicking? Is this clicking with anybody right now? Right? We just named some valence electrons. Okay, and then is it clicking? Is it? No, it's still not there. Okay, it's okay. So elements in the same column of the periodic table have similar properties, right? We talked about this before because they have the same number of valence electrons. That's what's new, okay? Valence electrons are impacting, right, those properties that these elements have here. So let's talk about this. Let's talk about this. Let's look at, that good old group alkali metals, right? The very first column, right? Not hydrogen, the very first column here. So what we want to see with alkali metals, right? We understand that alkali metals are metals and they got that positive one charge. Positive one charge. So what we're going to see is once we do our electron configuration, right? What we did earlier, guess guess what the outermost electron is? 2s1, right? In this case, that one electron is our outermost electron. Now, in this case, because it's the outermost electron, as we see here, right, we got 2s1, 3s1. So this entire column has one electron in the outermost shell. And because it has that one electron in the outermost shell, right, they're going to have the same properties. Okay. And we see this when we do the electron configuration, right? This one electron is in the outermost shell, all right? Because we understand, right? Well, for instance, if we look at lithium, the electron configuration is going to be 1s2, 2s1. So the 1s2, right, means that there's two electrons in the innermost shell. But the 2s1 is letting me know, well, I got one electron in my outermost shell, right? And because of that, we can see this here, right, with our electron configuration. Now, because it has those valence electrons, those are the properties that it has. And then we even look at the halogens, right? Halogens in this case have seven, right, valence electrons. So we look at chlorine. Chlorine has seven valence electrons, right? That means that it's going to have seven electrons in the outermost shell. Now, Dr. J, how do you know how many valence electrons elements have, right? Couple of ways we can find this out. We can either do the electron configuration, so we do it for chlorine, right? And if we do it for chlorine, do it 1s2, 2s2, etc. But I'm just going to focus on once we get up to this part, right? Once we get up to the very end of chlorine, we're going to see that we have 3s2, 3p5. So these electrons here are in the outermost shell, right? 3s2, 3p5. So we have seven electrons in the outermost shell, and notice where they are in that three row, right? The threes, 3s2, 3p5 for this particular chlorine. And that's really how there are in most cases, right? The outermost shell is your valence electrons. Okay. Now, another way that we can know is by looking at the periodic table for some instances. particular our main group elements. So if we look at 1A, 2A, notice, right, if you guys ever seen this on a periodic table, 1A, this is telling me how many valence electrons I have. I have one valence electron here. 2A, I got two valence electrons here, right, because I got two electrons in my outermost shell. We jump over here, right? We got 6, 7, right? We got 8, right? It's telling you how many valence electrons you have when you look at your periodic table, or if you do the electron configuration. Either way will be correct. All right, so now that we talked about valence electrons, let's just blow y'all head right now. All right. So when you're looking at your periodic table, that's the reason why I said the periodic table is about to be the greatest tool you have in chemistry, of course, right? So when you look at the periodic table, you can tell a couple different things by just looking at the periodic table. And one of those different things is letting you know exactly right what are your S, your D's, your P's, and your F's. Okay, so when I'm basically about to tell you, it's about to blow your mind. All right. So you notice, right, when you do your electron configuration, for example, everything that ends, right, in this case, for example, if we look at lithium, lithium is 1s2, 2s1. 2s1 is letting me know, right, I got one electron in my 2s shell. Now, let's look at our periodic table, right? It's all about placement. All of my S, right, things that end with my S's, notice, right, that they're ending in group 1A and group 2A, right? My alkali metals and my alkaline earth metals. They all, right, have similar properties. Now we understand, right, because of valence electrons, alkaline earth metals have two electrons in the outermost shell. Alkali metals have one electron in the outermost shell. And notice, right, their placement on the periodic table. They're on the far left side, right? These first two columns are always going to be S block elements, right? It's kind of, is it clicking, y'all? Is it clicking? If we go over to this side, the P blocks, the P's, when we do our electron configuration, they're always going to end in P's. All these elements are always ending in P's. Okay? If we look over here in the middle, the D blocks, all the transition metals end in D's, right? These are D block elements. And then if we look at our lanthanides and acinides, right, these are F block elements, right? All of them ending in F's. Okay? This is a key thing when we're thinking about the periodic table. It's the greatest tool you can use in chemistry, right? It can tell you specifically, right, now that you understand about your element, right? I understand, right? If I look at group one, for example, potassium. Potassium has one valence electron. I understand that now because it's in group one. It's an alkaline metal, but also the electron configuration is telling me, right, 4s1, that means that I got one valence electron. And because it's an S block, it's over here. It's placed over here. So once again, these three things right here I'm about to go over is going to really make the periodic table make sense now. The main group number corresponds to the number of valence electrons. So in this case, 1A, one valence electron, 2A, two valence electrons, 3A, three valence electrons, 4A, four valence electrons, 5, etc., 6, 7, 8, right? That means that those are the valence electrons. The length of each block is the maximal number of electrons the sublevel can hold. So if we look at the length of the block, for example, S blocks 1, 2, there's two columns. S's can only hold two electrons. Whoa. Blowing your mind right now. P, 1, 2, 3, 4, 5, 6. They can only hold 6 electrons. D, right? D can hold 10. F holds 14, right? I'm not about to count all that. All right. But basically, right, our periodic table is giving us value. Okay. And a period number corresponds to the principal energy level of the valence electrons. So when we're talking about the period number, we're talking about the rows, right? The rows. So if I look at my first row, it's going to tell me my principal quantum number, the principal energy level. If I look at 2, guess what? All those have twos, threes. All those have threes, fours. All those have fours, five, six, seven, etc. Right? It's telling you exactly what you need to know on this periodic table. Right? So this is how you guys can look at that. Look at that periodic table, know what you're looking at, and know how to use that now. Now, this is a little side note. This is a little side note. Transition metals, I've been telling y'all they are weird as heck. Okay, they are weird as heck. Now, this is just something to know going forward, all right? When we talked about electron configuration, the 4s sublevel is lower in energy than a 3D. Therefore, the 4s will fill before the 3D. Now, some of the transition metals do not follow the electron configuration rules in this case, all right? But we want to understand when we were talking about those energy levels. Let me go back. All right, so when we look here, right, the energy levels 1s, 2s, 2p, 3s, right? The order of our electron configuration, 3p, and you would think it'd be 3D, but that's not the case because the 4s orbital, we understand s's are lower in energy, so it's actually going to be lower than our 3D orbitals. So this is the reason why 4s will be coming before 3D, followed by 4p. Then we have another situation where our 5s energy level is actually lower than our 4D energy level. Because we got to understand, S's are the lowest, D's are the highest energy level, okay? So when it comes to the periodic table, that will impact, okay? That will impact. So we can see some different examples here. Now, how do they find this? Basically, there's a lot of experiments that have been done, okay? So they've done it all for you guys, all right? So these are the electron configurations for some of these transition elements.